Here's the Model 11.3 notes. This is page 2. So quick review of how we've looked at this in the past. In modules 8, 9, and 10, we used the area under the normal curve to represent a percent of a population. If you remember, we said, hey, between one standard deviation below and one standard deviation above, we had 68%. So this is minus one standard deviation plus one. And then we did the same for 2 and 3. Now, moving forward, we're going to look at that area under the curve as a probability. Okay, the probability that somebody is less than a certain height, the probability that somebody has an IQ greater than a certain number. Okay. So real quick, we want a review of how to round. We want to make sure that all probabilities are rounded correctly to the nearest 10,000th, which means 4 decimal places. So we are always going to look at 1, 2, 3, 4 places, and then we're going to take a look at the number in the 5th place. If the number is 5 or above, we're going to round up. If it's 4 or below, we're going to keep that value the same. Okay? We talked about on page 1 how a z-score tells you how far away from the mean a data value is, counting by standard deviations. Okay, so anything above the mean should have a positive z-score. Anything below should have a negative. Okay. Formula for z-score is always going to look like this. This is going to be our data value. I'm going to write it like this, and then I'll put it in symbols in a minute. Minus the mean has to be subtracted that way, so it ends up positive if the data value is above, negative if the data value is below, and then we're going to divide by the standard deviation. Which means if we are talking in terms of populations, you may see it like this: data value minus the mean all over the standard deviation. If we are talking about samples, we will see it like this. Again, same computation in different situations. Okay. So we have a couple of things to discuss in terms of our normal distribution. It is symmetric about the mean, which means that if I were to cut it in half at the mean and fold it over on itself, it would be roughly the same on both sides. It's bell-shaped, so our mean is the same as our median is the same as our mode. Total area under the curve is always equal to 1, and that's important. We'll use that a lot. The area under the curve is interpreted as a probability. We said we were going to talk about it that way, and the curve extends to infinity on either side. So in a sample, yes, we may have the highest value or lowest when we're talking about an entire population. Sometimes you can find one bigger than your largest. So when we want to find the area under a standard normal curve, we're going to start by calculating the z-score, and the next page is going to give us some practice doing that. We're going to draw a normal curve and label that z-score. We are going to shade the correct region, less than, greater than, or between, and then we are going to use norm.s.dist, standardized normal distribution. And for that, we need our z-score. Okay. So below here, we have the formula and the help from Excel. The norm.s.dist function returns the standard normal distribution, which means we are going to enter a z-score, and it's going to return the probability. So we enter a z-score, This returns the probability. And we are going to use this in place of a Z table, which you will see referenced when you read through the text. A whole lot easier this way, a whole lot cleaner. We will not be using tables, we will be using Excel. Okay. So here's our syntax. You will see norm.s.dist. Again, the first time you plug that into Excel, if you are unsure, click on that blue hyperlink. It will take you to the help and explain what you've got going on. You're going to enter your z-score. And then this cumulative. This means that we want to sum all of the probabilities up to that number. And we're going to talk about this a little more on the next page. This will always be a 1. Remember how we used the binomial distribution, binom.dist? It was always a 0. We wanted the probability at a given value and just that value. When we talk about our normal distributions, this will always be a 1. We want an accumulation of probability, so up to the value that we're looking at.